Welcome to the Deep Dive, your essential shortcut to navigating the complex and, let's be honest, often chaotic world of cutting-edge technology.
Especially now.
Especially now. Today, we are plumbing the depths of the core infrastructure that's really enabling this whole AI agent revolution. We're talking about the vector database.
And specifically, we're doing a really deep, detailed analysis of one of the leaders in the space, Milvus.
Right. So I think to set the stage, we have to talk about this fundamental shift that's happening with data.
Yeah, I mean, we are witnessing a complete change in how knowledge professionals interact with their data. For decades, the engine of any enterprise was structured data.
The neat rows and columns.
Exactly, your SQL tables.
Uh,
But that world is shrinking, and it's shrinking fast. Today, something like over 80% of all data generated globally is unstructured.
And that's the mountain of stuff, right? The text documents, the internal meeting videos, the audio recordings, all those research papers.
All of it. The messy stuff.
And that explosion of unstructured data is precisely why the old methods of information retrieval, simple keyword matching, text indexing, they've just become ineffective.
They're broken. Yeah. If you're a lawyer and you're handling millions of legal cases, or maybe you're a researcher compiling a century of academic papers, you just can't throw that corpus into a spreadsheet and expect a useful answer. It doesn't work.
It's not going to happen.
And that's where the promise of this whole era comes in with the rise of the AI agent and generative AI.
Right. These systems are promising to do high-level cognitive work for us, finding those hidden connections, synthesizing reports, inferring insights you wouldn't see otherwise.
But the large language models, the LLMs that power these agents, they are critically limited by their memory.
We've touched on these limitations before, but it's probably worth restating them because they're so central to this whole discussion. Let's just state the two main flaws that prevent LLMs from being, truly effective professional partners.
Okay, so first, the LLMs, what's called parametric memory is static.
It's frozen in time.
It's frozen. It's the knowledge it learned during training, which means the information it has about the world is immediately outdated. It doesn't know what happened yesterday in your company or in the legal world.
And the second one is, for me, even more critical for a knowledge professional.
Well, absolutely. The context window. It's physically small. You cannot just copy and paste a professional's entire proprietary knowledge base, that lifetime of private documents, research, client data. You can't put that into a prompt box.
It just doesn't fit.
It doesn't fit. So the AI agent can't operate without being able to reference that massive private corpus of information.
And that bespoke, specialized knowledge base is the unique competitive advantage for these individual experts and the small knowledge firms.
It's their secret sauce.
Exactly. So if the AI agent can't access that knowledge efficiently and reliably, then the agent is, for all intents and purposes, useless for high-stakes work.
And this is where the vector database steps out of the shadows. It finally becomes this piece of crucial infrastructure. It serves as the agent's long-term memory.
Okay, so it takes all that messy, unstructured data, the PDF, the PowerPoint, the transcript.
It converts it into these high-dimensional vector embeddings, and then it stores them. This allows the agent to retrieve information based on semantic similarity, or, based on meaning, not just keywords.
It's the bridge.
It's the bridge. It closes that gap between the LLM's vast general knowledge and the professional's very specific proprietary domain knowledge.
So our mission today is to really deep dive into Milvus. This is one of the leading open source VectorDB projects, and we need to look beyond just its feature list.
Way beyond.
We need to analyze its incredibly complex cloud-native architecture. We need to understand that intense market debate that's swirling around it. And most critically, we need to show how this piece of infrastructure is actually deployed to empower individual experts, the lawyers, the researchers, the creative professionals, and those boutique consultants to fundamentally augment their knowledge work. Okay, so let's unpack this journey. To really get why Milvus is designed for this massive scale and this kind of enterprise rigor, we have to start with the origins of its founder, Charles C. or Shi Chow.
Yeah, you absolutely have to. He brings what we are calling Oracle DNA.
And that history is non-negotiable in understanding the design philosophy, isn't it?
It's everything. She spent 6 years completely immersed in the enterprise database world at Oracle's U.S. headquarters. And he was working as a founding engineer on the massive Oracle 12c multi-tenant cloud database project. So when your foundational experience is at the absolute pinnacle of RDBMS technology, the standards you set for yourself, for stability, for robustness, for enterprise-grade performance, they are just inherently different.
So from day one, he wasn't thinking about simplicity or quick deployment. He was optimizing for institutional scale.
And long-term stability.
Hmm.
He saw the inevitable structural limitations of traditional relational database management systems when they were confronted with this shift to unstructured data.
So he saw the writing on the wall.
Precisely. RDBMS is fantastic for transactional integrity and structured query language. But trying to index and search billions of vectors for semantic meaning using an RDBMS framework, it just breaks down. It breaks down because of efficiency issues and index management limitations.
Okay.
So Xi's vision when he founded Zilliz back in 2017 was to keep that Oracle standard for high availability and stability, but apply it to the unstructured data problem.
So Milvus wasn't designed as just a simple utility.
No, not at all.
Yeah.
It was designed as a massive, future-proof data processing platform. It was built for the petabyte scale that he could clearly see was coming.
It's a really compelling origin story, isn't it? Importing that enterprise rigor into what was then a very nascent kind of chaotic world of vector search.
Yeah.
But the company culture is equally fascinating. It's embodied by what they call the Star-Lord ethos. Why choose the Marvel character Star-Lord as the founder's persona? What does that signal?
It really speaks volumes about the challenge they were facing. I mean, Xi wasn't building a product in a safe, known market. Vector search was, and you could argue it still is, this unexplored, uncertain part of the technological galaxy.
Right, the final frontier.
Kind of. And the Star-Lord metaphor, which they take from the Guardians of the Galaxy, it emphasizes two things. First, you succeed through a team of individually flawed experts, which is a great metaphor for the open source community and their dev team.
Okay.
And second, it's about being comfortable constantly exploring the unknown. They don't have a secure home base.
So this means they have to rely very heavily on the open source model and community contributions to break through all that technological uncertainty.
Yes, and that becomes a key tension point in the current market, which we'll get to later. But it creates this culture of agile evolution and really fearless exploration. And you can see that ethos reinforced in their naming convention, which is kind of unique. They name all their related projects after birds.
What's the symbolism there?
It symbolizes freedom, foresight, and agility.
Let's elaborate on some of those names because I think they help solidify this philosophical direction they're taking. We should start with the core product itself.
Okay, so Milvus. Milvus itself is the Latin scientific name for the kite.
A bird of prey.
A raptor, yeah. Known for its sharp eyesight, its speed, and its accuracy. So the idea is that it's designed to be this fast, precise raptor snatching the right vector out of a vast ocean of data.
I like that. And then, of course, you need the tools to actually feed that raptor the data.
Right, and that's towhee. Towhee is named after a North American bird that forages through leaves on the ground.
Looking for food.
Exactly. Towhee is their comprehensive ETL framework extract, transform, load. This tool handles the critical and, frankly, messy job of pre-processing all that unstructured data and generating the high-quality vector embeddings before they even enter Milvus.
And by standardizing that ETL process, they're ensuring the quality of the vectors themselves.
Which directly translates to the quality of the search results. Garbage in, garbage out.
Of course. And when you're dealing with a system this massively distributed, you must need tools for deep internal visibility.
Oh, absolutely. That's Birdwatcher. Because the underlying Milvus system is so complex, Birdwatcher is the essential debugging tool. It lets system administrators inspect and even modify the critical metadata that's stored in a Dolico, etc.
So it gives them a bird's eye view, so to speak.
Exactly, a bird's eye view into the intricate and dynamic internal workings of the whole cluster.
Is there anything for, people who are less comfortable with command line tools?
Yeah, they also have Attu. Attu is named after a remote bird sanctuary, and it provides a graphical user interface, a GUI, for monitoring the cluster status. It makes the complexity just a little more approachable. This whole ecosystem really shows a deep understanding that high performance requires high observability. You can't have one without the other.
So this entire philosophical obsession with scale and enterprise rigor, it leads us directly to the core technical reality. The architecture of Milvus 2.0. And I think this is the segment that has to clarify why Milvus has such immense power, but also why it attracts such intense criticism.
It's the heart of the debate. The transition from Milvus 1.0 was, it was revolutionary. Version 1.0 was monolithic.
Meaning everything was just bundled together?
Tightly bundled. It scaled vertically, bigger machines, but it was basically impossible to scale horizontally or guarantee true high availability. The 2.0 shift, which happened around 2021, adopted a fully cloud-native approach.
And what was the single biggest design principle that unlocked that flexibility and scale?
Complete disaggregation of storage and compute.
Okay, that's a key phrase.
It's the defining characteristic of modern large-scale data systems. You are decoupling two resource demands that have historically fought each other. Data capacity becomes separate from processing resources.
Can you help the listener understand the practical benefit of that? Like for a firm that's actually using it.
Sure, imagine a law firm. They have to archive massive amounts of older case files. That is a very write-heavy data ingestion process. It requires immense storage capacity, but maybe there's very low immediate read demand for those old files.
Right, they just need to be stored safely.
Exactly. So they can scale their low-cost storage capacity indefinitely without needing to spin up expensive computational or compute resources.
Okay.
Conversely, if they enter a period of high-traffic analysis, maybe a big case is active, they only need to scale the query nodes, which is the compute part, to handle all the read demands, and they can keep their storage costs minimal.
So that independent scaling is essential for cost-effective, fluctuating professional workloads.
It's critical. To achieve that flexibility, though, Milvus requires a highly complex four-tier distributed architecture.
Okay, let's break down this complexity. We have to do it layer by layer, starting with the outer layer.
So the entry point is the access layer. This is composed of what they call proxy nodes.
And what do?
They're simple, stateless gateways. They're just responsible for managing incoming user requests, doing some preliminary validation, and then routing the reads or writes appropriately across the cluster.
And because they're stateless.
They can be scaled horizontally and instantly. You can spin up more of them to handle enormous traffic surges without compromising the stability of the whole cluster.
Okay, so that's the front door. Next, we move to the control plane. This is the brain of the operation, right? The part that dictates how all the distributed work gets done.
That's the coordinator layer. And it's not one thing. It's a collection of specialized control nodes, and each one has a very specific mandate.
Okay, walk us through them.
You have the root cord, which is kind of the global manager. It handles data definition, language DDL operations, like creating or dropping collections, and it ensures overall cluster consistency.
Got it.
Then there's the data cord. It manages how the data is segmented and coordinates how that data is distributed across the worker nodes.
Okay.
Then the query cord manages the search topology. It distributes the search tasks to the query nodes. And finally, the index cord schedules and manages all the index creation tasks.
Wow, that is a lot of specialized management, and all of these coordinators, they have to rely on a single source of truth for their system state, correct?
Yes, and that's a critical point. They all communicate and maintain system consistency via shared metadata stored in etc.
etc.
This reliance on etc. for state management is key to Milvus's resilience, but also, as we're definitely going to discuss, a major source of operational headache.
Okay, moving on, we have the engines that do the actual work, the worker layer.
This is where the bulk of the processing power lives. The query nodes are the heart of the search process. They're the ones executing the vector similarity searches.
Right.
The data nodes handle the reliable storage of newly ingested data, converting those log streams into permanent data segments. And the index nodes are the resource-hungry components that use CPU or GPU power to build and optimize the vector index structures, like HNSW or DiskANN.
And the brilliance of this layer is that these three functions,
They scale entirely independently. You can have 100 query nodes and only 10 index nodes if your workload is read-heavy.
And finally, we get to the foundational layer, the storage layer. This uses a key philosophical approach that really differentiates it from traditional systems.
This is the log as data philosophy. It's adopted from distributed data systems like Kafka and Pulsar, which people might be familiar with. In Milvus, all data changes, insertions, deletions, updates, they're first written as an immutable sequential log stream to a reliable message storage system.
So Pulsar or Kafka.
Right. And that log becomes the authoritative source of truth.
Why is making the log the source of truth such a fundamental shift from, say, a traditional RDBMS?
Well, in an RDBMS, data is written directly to disks, and transactions have to be ACD compliant, atomicity, consistency, isolation, durability. The log as data model, on the other hand, guarantees durability and real-time processing in a distributed environment by allowing for immediate recovery and rewindability.
So if any worker node crashes during a write or an indexing process,
It hasn't lost the data. The immutable log is still there. The node can simply reconnect to the message stream and replay the log from the point of failure. This ensures complete data consistency and real-time coherence across the entire distributed cluster.
And where do the actual data files and indexes live?
The actual data segments and the huge index files are then stored in low-cost, durable object storage, like Amazon S3 or Minio.
That detailed architecture demonstrates just immense technical ambition. It's built for petabyte scale and uncompromising reliability.
It is.
But here is the paradox. That scale comes with a very high price. And we have to address the persistent criticism of Milvus regarding its complexity and the operational burden.
The criticism is often framed as microservices hell.
Right. For an engineer who's deploying Milvus on-premises, they aren't just deploying one system, they're deploying and managing 4 tightly coupled distributed systems.
Exactly. You have Milvus itself, but it has to be run alongside, etc., for the metadata, Pulsar or Kafka for the log streams, and Minio or S3 for the object storage. That is a massive resource commitment.
And that tight coupling is the Achilles heel, isn't it?
It really is. If etc., which handles the entire state of the coordinator layer, runs out of disk space, the whole Milvus cluster can just seize up. It can parallelize itself.
Wow.
Or if a partition in Pulsar becomes temporarily unavailable, Milvus can immediately stop accepting writes. So the engineers managing this infrastructure, they have to monitor the logs, the health checks, the performance metrics of all 4 systems simultaneously.
Which demands a specialized and probably highly paid infrastructure team.
It does. And that dramatically inflates the operational cost.
But the question has to be asked, is this level of dependency truly necessary? Or is this, as some critics suggest, a case of over-engineering?
The cow slaughtering knife to kill a chicken analogy comes up a lot.
I've heard it.
For a use case under, say, 10 or 20 million vectors, critics argue this architecture is just total overkill. The distributed nature inherently introduces network latency and overhead between the 4 components.
So a simpler solution might actually be faster for smaller loads.
It can be. A simpler integrated database solution, or even one of the lightweight dedicated databases written in a language like Rust, can handle that scale with much higher efficiency, significantly less resource consumption, and vastly simpler deployment.
So if you're a small startup or a boutique consulting firm, the immense resource overhead and the sheer effort required to maintain this complex Kubernetes cluster, it might just consume any performance benefits you get.
Yeah, absolutely might. And finally, there's the barrier to entry related to debugging, which is significant.
What do you mean?
The main configuration file, milvus.yaml, has over 500 parameters.
500.
Over 500.
Yeah.
And when a failure occurs, the resulting error message is often opaque. For example, you might get an error like, root cord client mess key not exist.
And what does that even mean?
Exactly. It requires deep core developer knowledge to interpret what state consistency issue just occurred within the distributed coordinator layer. While Birdwatcher helps, it's still command line based and requires expertise. It just creates a very steep learning curve for new users.
Okay, so we've established the intense technical complexity of Milvus and the equally intense operational critique it faces. Which brings us back to the core justification. If it's this complicated, why on earth would you use it?
And the answer is that its complexity is necessary for certain specialized, high-stakes knowledge augmentation tasks for individual experts and small firms.
Okay, so for the professional who needs a persistent, highly reliable brain for their AI agent, a brain capable of scale and specialized filtering Milvus is indispensable.
Precisely. It transcends being merely a database. It becomes the agent's specialized long-term memory complex.
Let's detail what that memory complex really means. The agent needs to store and recall more than just facts, right?
Much more. The agent must store semantic memory, that's the facts, the knowledge, the documents, and also episodic memory.
Which is?
The experiences, the context of past interactions, the results of past operations. By storing all of this as high-dimensional vectors, the agent can retrieve not just based on keywords, but on meaning, on intent, and on context.
Can you give an example of that?
Sure. Retrieving a meeting transcript based on a really vague query like, hey, tell me about the time we talked about that budget issue regarding the tricky client. A keyword search would fail on that. A semantic search can find it.
And the learning loop is crucial here. The agent doesn't just retrieve information, it has to learn from its own output.
Yes, that's the reflection and reinforcement mechanism. An AI agent, after it generates a response or maybe a legal brief, it can use an internal LLM as a judge to generate a self-critique.
So it grades its own homework.
It does. This reflection might be something like, my previous answer was too abstract and it lacks specific statutory references.
And that critique, that piece of reflective learning, is immediately vectorized and stored back into a separate collection in Milvus.
Correct. It creates this perpetual, cumulative learning experience. The next time the agent gets a similar high-stakes query, it retrieves the relevant source documents and it retrieves the past reflective critique. This allows it to automatically self-correct and improve its output quality.
So its performance spirals upward rather than just plateauing.
Exactly. And Milvus is the stable, permanent store for all of this institutional experience.
All right, let's move into our first deep application scenario, legal experts. In law, the stakes are, well, existential.
They really are. Precision, reliability, and factual accuracy are completely non-negotiable.
So what's the fundamental problem for them with this technology?
The fundamental problem is that pure vector search can be dangerously semantic.
What do you mean by dangerously semantic?
Well, if a lawyer searches for documents related to breach of trust, a dense vector model might retrieve documents about embezzlement or fraud because the underlying concepts are semantically similar.
But legally, those are very distinct terms.
Catastrophically distinct. Confusing them is a disaster for a client.
So just relying on dense vectors for high-stakes professional work introduces an unacceptable level of risk. The solution has to be much more sophisticated.
It requires multi-vector hybrid search, which is a specialized capability that platforms like Milvus offer.
Okay, what is that?
The agent uses two types of vectors at the same time. First, you have the dense vectors, often created by a specialized model like Lawbert, and they capture the nuanced context and sentiment of a legal ruling.
Okay, that's the meaning part.
That's the meaning. Second, you use sparse vectors using techniques like BM25 or Spladeway to guarantee exact keyword matching.
So the sparse vector ensures that specific critical legal terms like statute numbers, Article 356, or the exact wording of a contract clause, or even the client's name are always found, regardless of the semantic similarity.
Exactly. The hybrid search combines the results from both methods, maximizing both contextual relevance and factual accuracy.
Is that it?
Not quite. This combination is often followed by a crucial third step, re-ranking. A cross-encoder model then reviews the top retrieved chunks, verifying their contextual fit one last time before the information is passed to the LLM for synthesis.
So it's a three-stage process to elevate the reliability to the level required for legal work.
You need that level of rigor.
And the efficiency of the query is also critical, right? Especially with highly structured legal documents. They need to filter by structured criteria before searching the unstructured content.
This is where metadata filtering optimization is absolutely key. Legal documents are rich in structured metadata. The date of filing, the specific court, the judge, the case type.
And vector search is computationally expensive.
Very. So Milvus is optimized to efficiently filter the documents first based on that structured data, for example, only searching documents where metadata year, 2020, and metadata court, Supreme Court.
And then it performs the expensive vector search only on that smaller, pre-filtered pool of documents.
Which dramatically reduces latency and computation cost. It's a huge efficiency gain.
And given the extreme sensitivity of client data, there's just no question that legal AI has to operate with the highest possible level of security.
This necessitates private AI through on-premise deployment. Large law firms cannot and will not trust sensitive client documents to generalized cloud environments.
So they have to own the hardware.
You have to own the stack. By deploying the Milvus cluster on a private Kubernetes instance, they retain complete physical control over the data. Furthermore, they can fine-tune specialized models like Lawbert on their own private corporate legal documents, ensuring the system understands their specific internal jargon and case precedent without ever exposing that knowledge externally.
Let's pivot now to our second application, academic and humanities researchers. The challenge here shifts a bit, from legal precision to scale and discovery.
Right. It's about finding non-obvious multidisciplinary connections within these massive archives.
So a single document retrieval is often inadequate for serious academic work.
It's rarely enough. Researchers need what's called multi-hop reasoning. For example, a question like, how did 19th century German existentialism influence 20th century American postmodern literature, specifically regarding themes of alienation?
Wow, okay. That requires jumping between concepts, people, time periods.
A lot of hops.
This sounds like a job for relationships, which immediately makes me think of GraphRag, integrating vector search with knowledge graphs.
Absolutely. The vector database and the graph database, something like Neo4j, they play these perfect complementary roles.
Oh,
Milvus stores the vector embeddings of the key concepts, entities, and textual chunks. Those are the nodes for fast semantic retrieval. The knowledge graph stores the explicit, defined relationships, the edges between those concepts. Who influenced whom, when they did it, and how.
So how does the agent actually execute that complex multi-hop question we talked about?
Okay, so the agent starts by searching Milvus to semantically find the initial entities, existentialism, postmodernism. It then hands those entities off to the knowledge graph.
Which traverses the relationships.
Right, it traverses the edges to discover hidden related entities, say specific philosophers or literary critics who acted as a bridge between those two movements.
And then what?
Finally, the agent uses these newly discovered relevant entities to perform a second, highly targeted retrieval of the full contextual text chunks from Milvus. It turns the search into this powerful chain of structured discovery.
Now, for the individual researcher managing massive amounts of data, we're talking hundreds of gigabytes, maybe even a terabyte of digitized papers, it's a matter of economics.
Yeah, they can't afford enterprise-grade RAM servers. Cost efficiency is paramount.
This sounds like a perfect demonstration of where Milvus's advanced indexing technology, specifically DiskANN, becomes a game changer for the individual expert.
It really is. Traditional high-speed vector indexing, like HNSW, is very RAM-intensive. To search billions of vectors instantly, you need these enormous, very expensive RAM servers.
And DiskANN offers a compelling alternative trade-off.
It does. DiskANN is designed to store compressed vectors on low-cost NVMe solid-state drives, or SSDs.
Okay.
So while HNSW might offer marginally faster latency, DiskANN achieves near in-memory search speeds by intelligently minimizing disk access. It trades a tiny amount of latency or accuracy for a massive reduction in cost.
So it bypasses the need for those high-capacity RAM servers.
Completely. It effectively allows an academic to build their own personal big data research lab, containing their entire archive running at high speed, all within a reasonable personal or departmental budget.
Our third scenario, creative writers and novelists, seems so far removed from legal statutes and complex research graphs, but their need for consistency is just as critical, especially when they're building these massive, complex worlds.
Oh, absolutely. Their primary challenge is maintaining narrative coherence and character memory across a long-running saga.
Right. Think of a fantasy writer managing dozens of characters, intricate magic systems, complex branching event timelines over maybe 20 years of writing.
Forgetting a character's trauma or an item they acquired, that's a severe consistency failure. The fans will notice.
They will definitely notice, and traditional fixed schema databases are entirely incapable of managing this kind of fluid, evolving data. Character statuses change constantly.
And this is where Milvus offers a really elegant solution, using dynamic fields based on the JSON data type.
How does that work?
The writer's agent stores the evolving state of the world in a flexible JSON field that's associated with each entity, like a character or a place. So if a character's status changes from peasant to knight, or they acquire trauma after a battle, that data is instantly updated in the JSON field without requiring any kind of database schema migration.
And this enables real-time RAG fact-checking during the writing process itself.
Exactly. As the author drafts a new scene, the agent is monitoring the text in the background, querying the world-building Milvus collection, and proactively alerting the author to inconsistencies.
Give me an example of an alert.
The prompt might be something like, "Alert! You were describing the protagonist drawing a sword with their right hand, but the record states they lost their right arm during the Battle of Red Cliff in Chapter 42.
Wow. That transforms the vector database into a real-time continuity editor.
It does, and the augmentation extends directly into the creative process itself through style mimicry.
Okay, what's that?
For a long-running series, maintaining a consistent voice or tone is crucial. By vectorizing the author's past work, segmenting it into paragraphs and sentences, the agent can retrieve semantically similar phrases and mimic the author's unique tone and manner when it's generating transitional paragraphs or descriptive passages or maybe filling in dialogue gaps.
So it's using Milvus to maintain the aesthetic consistency of the entire body of work.
That's the idea.
We also see a really elegant integration here with personal knowledge management tools, PKM tools like Obsidian and Logsec, where a lot of writers already live.
Yeah, and that's key. Writers can stay focused in their familiar Markdown editors. Behind-the-scenes plugins and scripts are automatically embedding and storing those notes in Milvus.
So the writer drafts a note on a new character's backstory.
And that unstructured text is immediately vectorized. The writer gets to use the powerful vector-driven structure and recall for querying their creative world, but without ever having to learn complex database management.
Okay, our final scenario addresses the small knowledge businesses. We're talking boutique consulting firms, specialized agencies, multi-client research groups.
Right.
They need to leverage their internal knowledge for efficiency, but at the same time, they have to guarantee absolute data isolation for their high-value clients.
This is the problem of robust multi-tenancy within a shared infrastructure.
Yeah.
They need one powerful Milvus cluster to serve multiple clients, and they have to ensure that client A's data can never, ever be accidentally accessed by client B's query.
So how does Milvus achieve this secure, high-speed isolation, but within a single collection?
It uses partition keys. The consulting firm defines the client ID the client hid as the partition key for a collection that's storing all their project reports.
Okay.
So when data for client A is ingested, Milvus physically groups that data into a distinct physical partition on the object storage.
And the security mechanism is enforced at the query level.
Exactly. Every single search query must include the filter. Expert client add client ahead.
So it's
Right.
not optional.
It's mandatory. When this query hits the Milvus proxy, the system is engineered to only scan the physical partition associated with client A. This ensures absolute isolation between clients.
And it also provides a dramatic optimization in search speed, doesn't it?
It does, because the query nodes are working on a much smaller, dedicated segment of data. This makes multi-tenancy not just secure, but also highly cost-efficient.
And the productivity benefits for these firms must be immediate and quantifiable.
Oh, yeah. Think about automated proposal generation. Historically, generating a proposal required a partner to dig through years of successful past proposals, looking for relevant logic, pricing models, specific narrative.
A huge time sink.
A huge time sink. Now, an agent can instantly search the Milvus collection for logic and frameworks from successful, similar past projects, and it can generate a high-quality, customized draft proposal in minutes.
And what about using Milvus to structure the internal human expertise?
That's the hidden power here. Internal expert matching. Instead of relying on potentially outdated HR titles or skill surveys, the firm can vector analyze the actual content of their staff's written reports, their proposals, their internal memos stored in Milvus.
And what does that allow?
The agent can then recommend the absolute best internal staff member for a new project, the person who has the most semantic experience with a specific project type or technology, not just the person with the longest tenure. Milvus transforms institutional knowledge into actionable talent identification.
Okay, so we've established that Milvus provides these specialized high-power solutions that are uniquely suited for these high-stakes professional applications.
Mm-hmm.
But we cannot discuss this technology without confronting the intense market dynamics right now, the existential debates that are defining the vector DB landscape in 2024 and 2025.
This is the great schism. It's a battle between dedicated vector databases like Milvus and these integrated generalized database solutions.
And the single biggest competitive threat to the dedicated players is the rapid rise of PG vector.
Without a doubt.
Which is the extension for the post-Graceful relational database.
Oh.
What is the fundamental appeal of this integrated approach?
It's simplicity and integration. Those are the strongest sales points. For any developer who's already using Postgres, the instruction is simply just add a vector column.
That's it.
That's it. There's no need to spin up separate infrastructure, manage complex distributed dependencies, or learn a whole new set of query syntax. It lowers the barrier to entry instantly, and it drastically reduces operational friction.
And critically, these integrated solutions offer transaction guarantees that dedicated systems often struggle with.
That's the ACID guarantee. In R-Guide applications, you constantly need to join your vector data with structured metadata user IDs, timestamps, access rights. PostgreSQL provides native ACID transaction guarantees, which ensures that if you update the structured metadata, the vector data remains consistent.
So you're eliminating these massive data consistency nightmares that can plague systems where you're trying to synchronize a vector DB and a separate relational DB.
Exactly. It all happens in one atomic transaction. And the performance argument, which was the original reason for dedicated DBs, that's increasingly being neutralized, isn't it?
Absolutely. PGVector has made massive performance gains. They're integrating tools like PGVector Scale. They're adopting advanced algorithms like the high-speed DiskANN index technology. For a significant portion of the market, use cases up to tens of millions of vectors, the argument that you must use a dedicated DB for performance is simply no longer true.
Okay, then you have the other side of the competition, the lightweight dedicated challengers. The Rust Vanguard, specifically a player like Quadrant.
Right. If Milvus is the distributed battleship built for petabyte scale, Quadrant is the nimble, fast destroyer. It's built with the Rust language, which is prized for its memory safety and its speed.
And what's Qdrent's major advantage?
Single binary deployment. No complex dependencies, no etc., no pulsar, just one container ready to run. It's incredibly simple to get started.
And they aggressively target cost-sensitive startups through memory efficiency.
They do this by aggressively employing techniques like quantization, which compresses the vector data, minimizing the necessary RAM footprint. While Milvus often relies on RAM-intensive HNSW for pure speed, the Rust DBs offer a powerful, cost-effective alternative by minimizing the demand for expensive cloud RAM. That makes them highly attractive for a lot of startups.
So facing this strong commoditization pressure from the integrated giants and these lightweight challengers, what is Zilliz's survival strategy?
They recognize that vector storage itself is quickly becoming commoditized, so they're executing a platform play. They're evolving Milvus into an AI data platform,
Meaning?
meaning they're offering integrated solutions beyond simple storage. They're offering comprehensive RJ pipelines, re-ranking services, ETL tools like Tohi. They aim to provide an end-to-end knowledge workflow that integrated DBs like pgvector currently lack.
And this leads directly to their monetization strategy, which you've called the Zillaz Cloud Paradox.
This is critical. The operational complexity of open-source Milvus, that very microservices hell we detailed earlier, becomes Zillaz Cloud's strongest sales pitch.
So the problem becomes the solution.
In a way, the managed service basically says, Milvus gives you unmatched power and scale, but we will completely abstract away the pain of managing Kubernetes, etc., and Pulsar for you.
So they're charging for operational simplicity and guaranteed scale.
Exactly. They offer proprietary optimization engines and managed features in their cloud version that they claim guarantee up to 3x performance improvement over the open source distribution. They have to prove that the performance gains, the specialized features like hybrid search and multi-tenancy, and the total operational simplicity of the cloud version justify the subscription cost. That's how they convert those open source users into paying customers.
Okay, for the listener, the learner, who is ready to apply this knowledge and deploy an agent system, let's finish with an actionable implementation roadmap. Where do you even start when deploying an advanced system like Milvus?
The first step, and it's the one that is most often overlooked, is ETL and chunking.
Data preparation.
Data preparation. Data quality is search quality. You have to use robust parsing tools like unstructured or llama parse to reliably extract clean text from complex documents, PDFs, nested markdown, contracts, before you even think about embedding.
And the chunking strategy can't just be arbitrary. I mean, simple character count splitting is a recipe for context failure, isn't it?
It's the worst. It has to be semantic chunking. You need methods like recursive character text splitter that intelligently split documents by meaningful boundaries, paragraphs, sections, or headings. The goal is to ensure that every vector chunk contains enough complete preserved context so that when it's retrieved, it provides a meaningful answer without forcing the LLM to synthesize information from two disparate broken chunks.
Poor chunking is the #1 cause of RAG failure.
By far.
Okay, so once the data is prepared, choosing the correct deployment option based on your scale is essential.
Right. For an individual expert who's just prototyping or building locally, use Milvus Lite. It's a simple Python library, single process, no external server requirements. Super easy.
And for small teams?
For small teams or demonstration environments, Docker Compose provides a simplified, single container deployment of the entire distributed system. But for enterprises that demand high availability, massive scale, billions of vectors, and those specialized features, you must commit to the distributed Kubernetes setup or, more conveniently, Zillaz Cloud.
Finally, RAG systems are prone to drift. They require constant refinement. We need continuous quality evaluation.
You absolutely must instrument the system using objective evaluation frameworks like RAGAS. That's RAGS, RAG assessment.
And what does RAGAS do?
RAGAS helps you measure the quality of the RA pipeline end-to-end. We focus on key metrics like context relevancy. Was the retrieved document chunk actually necessary for the answer? And faithfulness.
And faithfulness is?
Did the LLM's final answer stick strictly to the facts retrieved from the vector DB, avoiding hallucination? This objective, measurable feedback is crucial for creating a continuous integration, continuous deployment, a CI/CD pipeline for your RAG system. So you're constantly refining the prompt, the chunking strategy, and the embedding model.
We have executed a full deep dive here, covering the ambitious Oracle-grade origins, the spectacular complexity, and the highly specialized utility of Milvus. It functions as this crucial, robust, infinite memory storage. that enables AI agents to move beyond simple chat and actually perform high-stakes knowledge work for professionals who require those specialized features, like hybrid search and multi-tenancy.
Our analysis really confirms that Milvus is a powerful cloud-native engine that delivers specialized features, things like DiskANN for cost efficiency, hybrid search for reliability, that are genuinely essential for the unique demands of high-stakes legal, research, and consulting knowledge work. These are areas where simpler databases simply cannot guarantee the necessary scale and precision.
But the narrative of Milvus, it really mirrors the history of distributed systems throughout computing, doesn't it? Perhaps most notably the rise of Hadoop.
That's a great comparison.
Hadoop brought distributed processing to the masses, but it became notorious for the immense complexity and operational cost required to keep it running smoothly.
Which makes Milvus a double-edged sword right now. For the organization that's dealing with billions of vectors or the niche firm that's building a highly customized multi-tenant AI platform, Milvus is an irreplaceable, powerful weapon. It's an engineering marvel born of that enterprise Oracle standard.
However, for the large majority of users, the startups or the firms dealing with millions of vectors and prioritizing simplicity and ease of deployment, Milvus risks remaining the epitome of over-engineering.
Unnecessarily complex and costly to run when you measure it against the increasingly capable integrated solutions.
Right.
The future of Milvus and Zilla's, I think, was on one single strategic question. Can Zilla's cloud completely and convincingly abstract away the deep operational complexity that's inherent in its distributed architecture?
So, will the Starlord ethos conquer the Kubernetes configuration nightmare and establish Milvus as the essential enterprise standard, the oracle of the AI era?
Or will these simpler integrated solutions like PDVector and the lightweight Rust legions like Qtrend supersede it by offering sufficient performance without all the operational pain?
And that is the critical choice every knowledge professional has to face when deploying their AI agent infrastructure today.
It's the central question.
Thank you for joining us on this deep dive. We look forward to our next plunge into the technologies shaping our world.